Hello guys and welcome to my first physics video here on my channel. Today we're talking about kinematics, so the motion of bodies. In particular, we're going to consider the motion of a very simple object, a point particle. And a lot of things can be approximated as point particles, for example the motion of a planet. We don't need to take into account all the complexity of the atoms of the planet. Most of the time we can consider a planet as being a point particle, a car as being a point particle, and various objects as being a point particle. So here I've drawn a path. As you can see, there's some pointers, some point particle going from A to B following this trajectory. Now I've drawn this because this is the essence of kinematics. But this is not just a simple basic description of the path you've taken. For example, I measure all the positions you took, measuring at what time you were in some particular location, and I record them, and that's it. Because knowing something about the motion, we can predict what's going to happen next, so the path you're going to follow next. Now, this is obviously a very complex scenario. We have this crazy curve, but we can analyze this using simple objects, simple mathematical entities and tricks by the end of this series. But firstly, we need to find a way to record these positions. So what we can do is to introduce a grid, an XY plane. Because as you can see, we cannot express the position, the y coordinate as a function of x, because this is not a function. And this is because the motion along x doesn't care about what the motion along y is. So we need to describe them separately using two numbers. So we're going to specify at each time a position x and a position y. These two values together gives us the position, and we're going to express this as a vector, because a vector, the vector r, is called the position vector, and is said to have x coordinate x of t, and the y coordinate is y of t in Cartesian coordinates. Now we're talking about 2 dimensions, because going from 1 to 2 dimensions is a bit difficult compared to going from 2 to 3 dimensions. From 2 to 3 dimensions is straightforward, and we're also going to get to 3 dimensions, but later on in the series. So we're going to stick with 2 dimensions for now, so motion in a plane. And this is the position. So for every time t, there's a particular x and a particular y. Now the motion along x is independent on the motion along y. This might seem weird because, for example, if you consider this is the x-axis, this is the y-axis, a stone thrown from this point, it could be a mountain or something like that. If you throw a stone, you get a parabola like this. So you might think, well, this is a function, y is a function of x. For every particular value of x, we get a value of y, that's a function. So we can express y as a function of x. But the motion along x and y is independent. And this is the case because the motion y doesn't care about what the motion along the x-axis is, and x doesn't care what the motion along y is. We simply know that, we're going to see later on, that there's some acceleration in the y direction, the x direction, there's only the initial speed, and the motion along x give rise to this parabola. But that's only because the conditions on the 2 axes are different, and put together they give us this motion, but x doesn't depend on y and y doesn't depend on x. In this case you might express it as a function, but the motion along the axis is independent from one axis to the other. We're basically saying, okay, it's going with constant speed along x, and along y is just going with some acceleration, and we're going to see how it works. If we throw a stone standing still without giving some throwing it with some velocity in the x direction, the ball goes up and goes down again. So that's something I really wanted to spend a couple of seconds talking about. Now, and that's the description picture. The motion can be described by this vector, so a couple of numbers, and those two numbers are expressed as a function of time, because for every particular time you are in a particular location. But then we need something more to analyze our motion. In particular, if, for example, I'm standing here at this point, I want to know how fast am I changing my position? Well, that's an interesting question, and this question also helps us, analyze this motion. And this is what we call speed. So speed is the rate of change of position, and we can express it as a derivative, because derivatives are rate of change. So the derivative of the vector r with respect to time is what we call velocity, and this is also a vector, because what we do in Cartesian coordinates is just to take the derivative of these two components, so this vector as components v along x as a function of t and v along y as a function of t. Nothing too crazy, but this is important because this tells us how the position changes, and if we want to know how velocity changes, we introduce the derivative of the velocity, second derivative of position, that is acceleration. But we're not going to go any further, so taking higher derivatives, because acceleration in most of the cases is the highest derivative of position with respect to time we need. And this is a picture of kinematics. Of course, these are vectors, so sometimes it turns useful once you put your reference frame, so your x and y axis, because you need a way to measure them relative to something, so that's our origin. We want to express the position, for example, this position here, as a vector. The vector might be represented both as a point or an arrow. An arrow is convenient because I'll show you really what velocity is. And in order to do that, let me take a simpler path. So if we have y and x, this is our path. We want to know what the velocity vector is. So we take the position at some point at a certain time t, and we take the position at a slightly forward time, so t plus a small delta t. What's the velocity vector? Well, we need to take dr by dt, but what does it mean, this? Well, this is simply the limit as delta t goes to 0 of delta r by delta t. What is the difference of these two vectors? Well, let me draw it with the red marker. It's this vector here, and you can think of addition and subtraction of vectors as from getting to the origin to this vector, I can go straight or I can go along this path plus this path. So this equals to this plus this, and this difference is simply this minus this. Now, if we take the limit as delta t approaches 0, so this vector gets closer and closer, we get this vector, and this vector is tangent to the trajectory. In fact, velocity is indeed tangent to the trajectory of motion. For acceleration in any path is more complicated, but we're going to take a look at it in another video. Now, the interesting thing that is that this vector, we draw it here, but this should be drawn here at the origin, because we specify this vector using this unit vector along y called j, and this unit vector along x that we call y. Basically a linear combination of these two vectors. That means some number that multiplies j plus some number that multiplies I gives me any vector in the plane using the addition rule we've previously been talking about. So it should really be drawn here at the origin, but we can also draw it here. But remember, this velocity vector can be expressed as a linear combination of I and j. And this is what velocity is. Now, for this video, I think it's enough. I really wanted to give a broad introduction about the topic. Next video, obviously, we're going to get into more details, and we're also going to do a little bit more mathematics. We're going to play with maths to find some motions. For example, the circular motion. That's very interesting, and that helps us tackle all this difficult path. Yes, this is what we're going to do next. We're going to analyze motions using the notions we've learned so far. So if you enjoyed this video, please consider subscribing to my channel, share this video with your friends, and as always, thanks for watching this video. See you for the next video in this series. Bye.